couple of more weeks before we finish the semester. Practical considerations in modeling and heat transfer. So this is the week we are going to cover these items. It is chapter 7, practical considerations in modeling, and also chapter 13, which is the heat transfer. So we are here on Thursday, November 11th, Veterans Day. Of course, it doesn't affect us, but if you have classes, there is no school on Thursday. That is where we are. We finished our discussion on plane stress and plane strain problems, which was chapter 6. And next week, we will continue with heat transfer. And also we have our second quiz next week. So a couple of words about our quiz next week. We are going to have, again, on Canvas, 5 questions, 2 points each. It covers everything that we had since our previous midterm exam. Previously, we had our midterm exam. It covers beams. So we didn't do this one. So it would be the quiz next week. It would be on frames and grid, chapter 5, and plane stress, plane strain problems, chapter 6, and then again, it was continuation chapter 6. And what we discussed today about practical considerations in modeling, which is chapter 7. So it would be on the quiz, not this one, not chapter 13, and it is not heat transfer, but everything else that we did will be on the quiz. Again, 5 questions on Canvas, either short answer questions, or you calculate something, enter your answer. You can't go back, make sure that your answer is correct. Once you enter, you're done with that question, you go to the next question. Possibly 30 minutes, 40 minutes, 45 minutes. I have not made the test yet, but it would be 5 questions, each one 2 points, no extra credit. These are already small pieces. These are just 2 points. I have already broken down into these 2 points, so there is no partial credit for these questions, 2 points each. And it covers these items, 30 minutes, 40 minutes, 45 minutes. Canvas will show the timing. Make sure that your Canvas works. Make sure that you have access to internet. I cannot do anything if you have problems like this. If you are not sure, you can take the quiz on campus, but make sure that everything works fine. At 10 o'clock, you go to Canvas. You don't need to come to Zoom. Go to Canvas at 10 o'clock, take the quiz. Once you are done, whether it is 30 minutes or 40 minutes or 45 minutes, Canvas will show this. And then we will have our class at 11 o'clock. So 11 o'clock, we again meet on Zoom, and we will continue with heat transfer problems. I think that's all about the quiz I wanted to discuss. One question was, if you have, for example, if there is a problem, it is possible that I break down a problem into different pieces. So 2 points each. So, but it can be related to one problem. So pay attention to this one. When you solve it, of course, you have it. And then you may answer, for example, 2 different pieces or related to one problem. But the problem is clearly, it tells you what to do, and make sure that you answer it. There is no partial credit. So read it carefully and answer it correctly. All right. Any questions about the quiz? All right, no questions. Now, one more item about the project. The project you are working on on Wednesday. Again, we do not meet on Zoom or Canvas. You work on the project individually. One item is that applying the constraints, you have to pay attention in problems that we do in finite element modeling. We have to apply boundary conditions. Now, boundary conditions are two types. Whether it is load boundary conditions, you apply load, forces, moments, torques, or you apply displacement boundary conditions. These are constraints. Now, in a problem, you have to have some type of loading, and you have to have some type of displacement boundary conditions or constraints. Otherwise, we can't. The program needs to know where it is, needs some references at what point it is fixed or what point it has some specified displacement, and so on and so forth. So the constraints you need to specify, paying attention that if it is a two-dimensional problem, you need to specify some displacement in the x direction and some displacement in the y direction. If it is a three-dimensional problem, you need a constraint in the x, a constraint in the y, and a constraint in the z. So the program has some reference to these for displacement in these degrees of freedom. So whether it is displacement is 0, whether it is displacement is a specified displacement in any of these directions, but we need some displacement boundary conditions or constraints so the program can solve. Otherwise, it gives you, for example, fatal error because it doesn't know what is happening in the x direction. We cannot just apply force in the x direction and have no displacement boundary conditions. It needs some reference. So with reference to this point, that, for example, has a displacement of 0, then this point has this displacement. So pay attention to displacement or constraints that you specified for your problem, but create the model such that it represents the actual problem. This is the responsibility of a person doing finite element analysis, to come up with a set of constraints or loading boundary conditions so it very closely resembles the actual real world problem. All right, that's all I wanted also to discuss about the project. Any questions before moving on to chapter 7 and talk about practical considerations in modeling here? This is module 13, we are here. All right, no questions. So today I want to discuss 11 items with you. No formulas, no problem solving, of course, for chapter 7. This piece of our discussion before talking about heat transfer, but in chapter 7 is practical considerations. No formulas, no problem, just discussions, but important topics we are going to discuss, which guide you how to model and solve, do finite element analysis. All right, so 11 items I want to discuss. Item number 1, and I want you to participate, ask questions, feel free to participate and tell me about the experiences you have and mistakes that you made or any questions you have. Type of element is very important. You have to always select the right type of element. So far, we learned about bar elements that we use for trusses. We learned about truss bar elements that we use for trusses. We learned about beam elements. Beam elements we use for both beam problems and also frames. And then also we learn about the triangular elements we learned. These are for continuum elements, two-dimensional plane stress, plane strain problems. We use triangular, for example, elements. So selecting the type of element is very important. It depends on what type of element, what type of problem are you solving? Is it the beam problem? Is it the frame problem? Is it the truss problem? Is it the two-dimensional plane stress plane strain problem? Is the three-dimensional problem? So make sure that you know the type of problem and select the right type of element. Some programs, for example, like ANSYS, it has more than 100 different types of elements. It has a library of elements. So we have to know what problem it is and what element to select. So it models this problem very as close and as correctly as we can get. All right.
Professor?
But item number 1. Item number 2, boundary conditions. Pay attention. We discussed this a little bit now.
Professor?
Displacement boundary conditions and force boundary conditions. Make sure that these closely model their actual physical real world problem. Whether it is loading, if it is distributed, if it is concentrated, if it is varying, the same displacement, if it is fixed, if it has a specified displacement in any direction or so, apply them so that it is very close to what the actual real world problem is. Now, aspect ratio is another important topic. Look at this beam, cantilever beam. It is fixed here. And we are applying this distributed load here. 40,000 pounds total force distributed like this here. This is point A, point B. Now, let's select this element, analyze it a couple of cases. One case is we are selecting element like this. It has 12 inches. The total length is 48 inches and 8 inches. This element has a length of 12 inches by ½ inch. Now, a definition, aspect ratio, it shows AR here. Aspect ratio is the ratio of this long side divided by this short side. So 12 divided by half is 24. And we can select another aspect ratio. Let's select this side 6 and this side 1. So aspect ratio is 6 divided by 1 is 6. Another one, aspect ratio of 3.6. 3 by 2 inch. So this is 3 inch by 2 inch. So it makes it 3 divided by 2 is 1.5. And finally, this one, aspect ratio of 1.1. So we have several different aspect ratios. We want to compare to see what results we get. This one would be the worst one. This one, not good. Don't select aspect ratio, large aspect ratios. Stay close to 1. The closer you are to 1, the better your results will be. Let's look at some numbers here. This one, this is aspect ratio versus percentage error for the displacement at point A. Remember, this was point A here. Displacement of this one, this is error. This is aspect ratio. This is the exact solution. As aspect ratio is high, it is 24, which was case 5. The error here is negative 55%. Our deflection is 55% less than the exact solution. Another case, case 4, aspect ratio close to 6. Error is about, let's say, 25%. And aspect ratio as it is close, approaches 1. Let's say here, aspect ratio about 1. And we have just 5%, about 5% less than the exact solution. So you see that as aspect ratio approaches 1, our solution is more exact. Our solution is closer to the exact solution. As aspect ratio increases, our inaccuracy increases. All right, so this was one point I wanted to.
Hey, Professor.
Another point of discussion here. This table
Professor,
also shows the numbers.
Can you hear me?
Different cases.
No.
Different aspect
Professor?
ratio, 1.1 and 2.4.
Yo,
And we get, these are the
homie's
deflections.
is going, okay.
As you see here, deflection for point A.
Professor, can you hear us?
The audio is off.
Yeah, we're trying to talk to you.
Hello?
Let me see what the problem is. Well, I don't hear anything. If you have a question.
Professor, if you can hear me, I have a question.
Yes.
Cool. So what is like a reason that you would want a large aspect ratio? Like what are the arguments for a larger aspect ratio? Like why don't we always just use one no matter what?
Let me see, there was, I'm sorry, what is the question again?
In what like scenario would you want a larger aspect ratio? Like why don't we always have an aspect ratio of 1?
Always stay close to 1. We never want large aspect ratio. Don't do that. That's what we are saying, that this
So
is
there's
bad.
no consideration, like so we would never want an aspect ratio for any reason larger than 1?
No, but we can't. Of course, we cannot get exactly 1 because some problems, we want to stay close to 1. But of course, creating the mesh is also a little challenging. So we cannot make sure that all elements have aspect ratio of 1, but we stay close to 1. But we don't want a large aspect ratio. We never want that. But we do our best to keep it close to 1.
Okay, cool, thank you.
Sure. Our goal is to keep it close to 1. We don't want, but the problem is we can't always, I mean, the geometries are complicated. So creating the mesh is a little challenging. So we cannot make everything 1, but we stay close to 1. For example, as what you see here, what was this one aspect ratio of? We had 1.1, 1.5. These are fine, these are acceptable. But then going here, these are not good. But staying close to 1, as you see, the deflection, the percentage-wise. So here, the exact solution for, let's say, displacement is negative 1.52, negative 1.078. So if we are here, it is okay, but then it is not good. For larger aspect ratios, it is not good. But the better results we get when it is close to 1. Item number 4, again, a little continuation of that one possibly. Make sure that these elements are compact and regular shape. Avoid these extreme scenarios like this one, that what we discussed, for example, large aspect ratio, B divided by H, keep it close to 1. So this, if B is much larger than H, is not good. This one, if it's trapezoidal, for example, make sure H1 and H2, they are close to 1. So it is more irregular shape. This one, make sure this angle alpha and beta here, they are close to each other. It is not like this angle is 10 degrees and this angle is 170 degrees. So this would be very bad. Some programs actually give you warning. They give you, they tell you that this element, for example, is distorted too much. Element number, let's say 1500 is distorted too much. So it means that this angle and this angle, it is large. So the program gives you warning sometimes. So this is not good. And something interesting about this one, look at this one, tell me what is happening here. That's your job. Tell me what you think, what is happening.
It's a quadrilateral, but one of the points, one of the nodes is collinear with the other two, so it's just a triangle.
Very good, you're right. This was actually supposed to be a quadrilateral. Quadrilateral has 4 sides. This is 1, 2, 3, 4. But what happened, it turned out that these 2 sides became collinear, so it's along the same line. So let me make a drawing. Let me use the camera. You should see the camera on your screen. Am I right?
Yes.
Okay. Now let me make it. Suppose we have this element. This is this node here, this node, and so this is fine. But suppose that this node somehow comes along this one, and we create something like this. So this is a quadrilateral. This quadrilateral element is fine. We don't have any problems with this one. But something happened that this side this is one node here, and this one came and became collinear. These 2 sides were here. This one, it is not good. Now, why is it not good? Well, let me explain this a little bit more. This element that you see here, it has 4 nodes. Now, one of the assumptions in our finite element formulations is that there is a one-to-one mapping. Let me write one-to-one mapping. This assumption is important. Now, if we violate this one, then we don't get correct results. Now, what it means is that if you select 2 points in this element, let's say I select this point here and this point here, connect these 2 points, all the points along these 2 points along this line should fall within the element. This is the assumption of one-to-one mapping. So this is correct. If you select another point here connected to this one, so all the points along this line are within the element. That's correct. That's fine. But suppose this case, how to make this one, let's say like this. This is also a quadrilateral element, is it? This is 1, 2, 3, 4 sides and 4 nodes. This is bad, not acceptable. Why? Well, because if you select this point here and this point here, and then if you connect these 2 points, the points along this are not all of them within the element. You are exiting from this element and then coming back again. So that is not acceptable. We are violating the one-to-one mapping. So that is not correct. The formulation, we are violating the formulations that we had. So, so this is not acceptable. Now, a little bit more, see what is happening here. The discussion of having a regular type element is because of this. You see, when we have our aspect ratio, suppose we have this element. It's a long aspect ratio, it's a large aspect ratio. Now, the point is that when we do numerical integration, these types of elements, the B matrix, elements in the B matrix, they are functions of X and Y. So to find the element stiffness matrix, we have to term by term integrate. Now, integration is done by Gauss points. Now, the way that we do this, we select, let's do it in this color so you can see, the way that we do it, we select 4 points inside this to find the element stiffness matrix for this element. We select 4 points, evaluate this integral at these points, and then add them together. Then that would be the result of this by numerical integration, Gauss quadrature technique that we use. Now, we get better results if these distances are at far from each other, not like this. They are very close, and these two are very close. This is very long and very close. So like this, these Gauss points are not selected properly. Gauss are selected properly is, for example, for this one, we select at about 0.87. So we select this point here, this point here. So as you see, they are sparse. They are at a distance from each other. So evaluation of this gives a better result than this one. When we evaluate this one here, this and this, they are very close. So we do not get good results in numerical integrations. That's what we want, these elements to be of regular shape, so our numerical integrations give better results. All right, so now with this one, let me stop the screen sharing this video and go back to Canvas. So that was this discussion here, that we want them to be regular shape, not like these extreme cases. Again, numerical integration of these things do not give very good results when it is folding like this or this one. All right, item number 5. I said, how many items are we going to discuss today? How many items are we going to discuss today, anyone?
11.
11 items. 11 items. So that was number 4. Now, number 5, symmetry. Use it. Use it whenever you can. We discussed this symmetry in our class also before. But here, for example, this is a tensile test specimen. This is specimen that you see here. We are applying the tensile force here. Instead of considering the whole thing, just consider just 1/4 of this. A quarter of this will do the job. But when you consider symmetry, you have to pay attention. All the points along this would be on rollers, because these rollers allow these points to move in the X direction, but not in the Y direction. And these points along this plane should be allowed to move in the Y direction, but not in the X direction. So fix it in the X, allow it to move in the Y direction. And for this particular point here, at this corner here, this point will not move in the X direction and in the Y direction. This particular point is fixed here. But all other points along this are on roller. And this one, it is also on rollers to allow it move in the Y direction. So always use symmetry whenever you can, but pay attention that you have to put symmetry, you have to put them on rollers if you are considering symmetry like this. Another example is this one, this plate, for example, with this hole here, we are applying this tensile force. Instead of considering the whole plate here, we can just consider a quarter of this, but again, use rollers to model these two sides. All right. That was our discussion on item number 5, symmetry. Questions on this or move on? All right, let's move on to item number 6, subdivisions at discontinuities. Whenever geometry changes or whenever loading changes or whenever there are concentrated forces or moments, consider having a node at that point or for separating these regions. A couple of examples here. For example, we have a concentrated, yes.
There was a question about symmetry in the chat.
Question, why exactly do we use rollers for symmetry? Why do, well, here, of course, you see here, of course, in our class, we discussed this one. You see, these points, this point here can move in the X direction. Well, let me ask you a couple of questions so we can understand it better. These points along this line, points, can they move in the X direction when we apply this force here and here? Can these points along this line, can they move in the X direction? Yes or no?
Yes.
All right, you are right. Can these points move in the Y direction?
No, there's no force in the Y
No.
direction.
There is no, these points cannot move in the Y direction. So if we want to consider symmetry and use 1/4 of this, you see this hatched region, this is just that piece. This is just this hatched region. If you just want to consider analyzing this one, then we have to make up for breaking this. We are cutting this material here. We are cutting this material here and removing this. So we have to do something about this boundary condition. We have to do something to model this quarter the same as the whole piece, as if it was the whole. It's just 1/4 of the whole thing. If we want to model this quarter, it should behave the same as this here. And the same as this here behaves is that we have to see when we are cutting this, then replace it with something. You can't just cut this without doing something on this. We are cutting this material here. We want to consider this quarter part. So we are cutting this material. If you are cutting this, then we have to do some boundary conditions here. And what you told me, it can move in the X direction, but cannot move in the Y direction. So you have to put these rollers. These rollers are for this, just a terminology, meaning that they can move in the X direction, but they cannot move in the this allows it to move in the X direction, but doesn't allow it to move in the Y direction. The same as exactly what it was. And the same for here on this side also. When we are cutting this, we have to consider to do something about this. We can't just remove this without replacing it with something. So it behaves the same as if it was the whole part that we
Professor?
have. Yes.
If there was a load in the Y direction, would you still be able to use symmetry here?
No, we could not. It depends on what if it was, if it is a concentrated force, absolutely not. But if it is, let's say we are along the whole thing here or the whole thing here, then yes, we can also use symmetry.
So
if you
then
don't
what
allow-
would you replace the rollers with? Because there is now force in the y direction or movement in the y direction.
Well, if it was the case, so it would be the same as this one. So again, you have to see the behavior. You would consider the same as what it is here. So again, you allow this to move in this direction and this will move in the y. So the same as this one, actually. If you have a force all along this, you see, you have to have symmetry. You cannot have a force here and then balance it here and then nothing here. So it's not symmetric anymore. But if it is the whole thing on this side, it is you have a force in the y direction allowing this side the same as this one, then yes, again symmetry applies. Again, this side will remain. It can move in the x direction because of this force, and because this force and this force are in balance, so this will not force in the y. These points will not move in the y direction, so this is correct. And the same as this one. If you have a force here, it moves in this direction, but not in the y direction. So the same that you have here will apply for that case as well.
Got it.
All right. Any other questions about symmetry? All right, very good. Good questions. So this is this one. Now, discontinuities always whenever loading changes or whenever geometry changes or material changes, then you have to separate these regions. For example, here we have a concentrated force. So we should have a node here to define this at what point, where this load is applied. We need a node. Here, load is distributed, W1, W2. We have to separate this region from this region. This one, thickness of this piece here, you see this plate, it has two thicknesses, T1 and T2. You have to separate these two regions. Material changes, material 1, material 2. You have to separate them by selecting nodes along this. So this region is separate from this region. This problem, the implant, nowadays dentists do implants. It's more routine work for them, actually. This is the bone, this is the jaw, and then the dentist actually cut this, remove this, and implant a new material. I don't know exactly whether it is the material, possibly, I think, a titanium, possibly they use, or that was maybe expensive a little bit, but maybe different materials, but they use another material and implant it into the bone and put a post here. Then they put a crown on top of this one. So then that's it, and there's a new tooth now. But this is the implant. So this is a different material than the bone here. So we have to define this. So all these elements are different, they have a different material properties, and then we have to define these regions by these nodes. So they are separate from this base material. This one, you have to, of course, geometry is changing. So put a node here at this intersection. Another point here, you have a distributed load like this, triangular. And nowadays, of course, all these computer programs can model this, but sometimes if a program cannot model this, you can extend these elements outside of this structure itself, like this. So when you apply this load, actually this load will cause a load distribution on this structure, which is the same as this one. So this is also acceptable replacement in your modeling. This also resembles this one. But nowadays, these programs, all of them, like FEMA, ANSYS, all of them, you can define this type of distributed loading, and you don't need to extend these elements out like this. But the point here, it was to, whenever there are discontinuities or geometry changes or material changes or your loading changes or so, you need to specify nodes and separate them from each other. Now, element size. We did it many times in our activities. Remember, you were running the problem again, and we were saying, okay, well, this time now use half the element size, make the element size half, and then run it again. Remember, we did it several times. So, and you saw that the difference between these different cases when we changed the element size. What was it? When you were making this element size smaller, your result was more accurate or it was less accurate? Question for you. Anyone?
More.
More accurate.
More accurate. You are right. Element size. So make the element size, make the mesh finer around the discontinuities. Whenever there are holes, whenever there are discontinuities in the material, make the mesh finer so you get better results. Farther from where we have stress discontinuity, that's fine, but larger elements would be fine. But where stress is changing rapidly, whenever you have stress concentration, these are basically points where we have stress concentrations. So stress is changing rapidly here, have more elements. All right, so let's all right, now in general, we have two types of elements. One is called H element, and one it is called P element. Now, what is the difference? FEMAP, by the way, didn't have both of them. FEMAP just had H element. It didn't have P element. Now, what is this H element? Most programs have H element. This one means finer mesh, but low degree of polynomial to approximate the, let's say, displacement over this element, or low degree polynomials for shape functions we end up with. So this means finer mesh, more number of elements, but low degree polynomial to approximate the solution. P coding, on the other hand, says large elements, big size elements, but high degree polynomial. Now, this polynomial starts from, let's say, polynomial of second order, this quadratic equations. We start with polynomial of degree 2 or 3. We solve the problem, then we increase the degree of the polynomial, let's say, to degree 4. We solve it again. We compare this solution to the previous solution. We see that no, displacement changed a lot. So as we increase the degree of the polynomial, our displacement changed too much. So we say, okay, well then change it now to degree 5. We run it again. Compare it to the previous run. If the difference is too much, again, run it again, go to polynomial of degree 6, degree 4, degree 7, 8, 9. Usually these programs, I think, go up to 9. Although I think this lately I saw that I think a program like ProMechanica that exclusively uses P coding, I think it was up to even 12, if I'm right. But up to 9, I have used this, for example. And so it uses iterative procedures. The element is large, but it changes the degree of the polynomial to approximate the, for example, displacement here. So 2 types of approach that we have: H, small size elements, finer mesh, the degree of the polynomial is low. This one, large size elements, but high degree polynomial. But it has to converge. It starts always with the lower degree polynomial and then keeps increasing in different iterations, and it has to stop at some point. It compares it to the previous one and then see if stress or displacement or whatever design criteria you specify meets the requirements that you have specified in the program, then it stops it at that point. A program like ProMechanica, for example, just uses exclusively P coding. Most programs use H. Some programs have the option of either P or H, like ANSYS. ANSYS, there is a window opens, it tells you, is it H element or is it P element? So it gives you, but with P element, you have to always have ways to, for convergence, make sure that you check that it has converged. Otherwise, this solution is not acceptable. All right. Any questions, or are we ready to move on? All right, move on. Connecting different types of elements. Sometimes we have beam elements and we have a plate element. So these are, they have 2 different degrees of freedom. Degrees of freedom for a beam element is not the same as for this plate element. So what should we do? This is a beam. It has degree of freedom in the Y. And it has this displacement and rotation also here. So displacement and rotation. But this doesn't have rotation. This is a plane stress, plane strain problem. It has just degree of freedom displacement in the X and Y. No rotation degree of freedom. That's what the problem is. So how do we match them now? Well, one way to do this is to extend this beam into this one, so it can carry the displacements in the X and Y. So this moment can be transferred now here. Otherwise, this moment could not be transferred here because there is a rotation involved here because of this moment, and this cannot handle it like this. But here it allows this moment to be transferred like this. Nowadays, of course, programs, again, do not have this problem. They take care of it themselves. Before they had engineers doing the stress finite element analysis, they had to do this, sometimes even connecting this point to this point and this point, or extending it either way. But nowadays programs, they have a function, and even actually ANSYS automatically it does this. There is no problem with even specifying anything. You specify that this is the beam element, there's a plane element, and the program inside takes care of this rotational degree of freedom. All right. Finite element method. Question for you. Finite element method is an approximate method of solution of differential equations, or is it an exact method of solution of Abelian differential equations?
Approximate.
It's approximate.
It's approximate. It's approximate, but it doesn't mean that we should be skeptical about this. Absolutely not. With these advanced types of elements and with these computers with more memories and more accuracy, better algorithms, so they, in many cases, they match the exact solution. And those that do not match the exact solution, it is very, very close, and this is absolutely acceptable results we get. But nevertheless, always find ways to check and verify your results. These are numerical methods. After all, these are numerical methods. We have to always find ways to verify our results. And you did it in the activity you checked equilibrium. Remember from the beginning when we solved some of these problems, frames or so, I was asking to check for equilibrium. And you were checking the reaction forces that you were getting with the external forces and moments, and you were to make sure that our solutions make sense, our input were correct. So compatibility, check for displacement, check for whenever, all the time you were practicing with plotting deformed and undeformed shape. That's what I wanted you to see if it makes sense or not. That was all to verify your results. And finally, this is the last item. Convergence of solution, 2 points here, very important. Always accuracy increases as number of elements increases. So the finer the mesh is, the better results you get. The general formula is like this. And also, we talked about aspect ratio, keep it close to 1. Don't let aspect ratio of 20, 30 or so. These are absolutely not acceptable, and it is not correct. So these 2 points, you can see it from this figure. If this is displacement versus, let's say displacement, exact solution for displacement. As number of elements increases, you see that we are converging. Compatible displacement formulation. We are approaching the exact solution as number of elements increases. So that is what this point is. The finer the mesh, the better results you get. General formula. And the higher the aspect ratio, the higher your inaccuracy. That's all the point I wanted to say, these 11 points from this chapter 7. And this is the example that I showed you. This is the, we checked the aspect ratio of 24, 6, and we saw that the best when aspect ratio was close to 1.1. And this is the result. You see aspect ratio. You get better results when it is it approaches 1. All right. And the finer mesh here, you see that, for example, here, let me see number of elements. You see here, these are coarse mesh, but this is finer mesh, and aspect ratio is acceptable 1.2. So you see very good result. The exact solution is negative 1.152, and it is negative 1.1. So we get good results as the element size is smaller and the aspect ratio is close to 1. All right, that's all the 11 points I wanted to discuss from chapter 7 of our textbook. Any questions about these 11 items? All right, no questions, which means we are ready to go back to modules. Go back to modules. We are here November 8th here. We finished with chapter 7. Let's go to heat transfer. Our discussion on heat transfer. Heat transfer is not a prerequisite for this class, so I start from the beginning, although it is good to have this prerequisite of heat transfer. this would be our last discussion actually on, we finished with our discussion with solid mechanics problems. Now, time to switch to heat transfer problems, one-dimensional and steady state, the simplest one. If you don't have the prerequisite for heat transfer, that's fine. I start from the very basic. It's not very basic. We start and then we move on to also 2D later. But whenever you have questions, as always, feel free to ask. One-dimensional heat transfer problem. This is a wall. This is solid, a wall separating two fluids, fluid 1 at temperature T1 and fluid 2 at temperature T2. So this wall has length L separating these two fluids. This temperature T2, suppose it is greater than temperature T1, so heat will flow from the high temperature region to low temperature region. So here, from fluid 2 by convection to the solid. So this is the mode of heat transfer. In general, we have 3 modes of heat transfer: conduction, convection, and radiation. So convection is when heat transfer of heat between a fluid and a solid. Through the solid, heat is transferred by conduction. And again, from this solid to this fluid, it would be by convection again. So we have convection, conduction, and again convection. Now let's look at each one of them. Today we are going to look at finite element formulations for this one-dimensional steady state heat transfer problems, and then look at an example problem. That would be our goal today. For conduction, for this part, the equation that governs this behavior is Fourier's law. It says Qx is negative Ka dt over dx. This is the rate of heat transfer, Qx. Its unit in SI, it is kilowatt. In US customer system of unit, it is BTU per hour. Can anybody tell me what BTU stands for?
British thermal units.
Very good, you're right. This is British thermal units, and it governs the same as in SI kilowatt. This is the formula for conduction. K here is thermal conductivity, or conduction heat transfer coefficient here. Its units in SI, watts meter degree centigrade. US customer system of unit, it is BTU hour degree Fahrenheit. This is area. So this is area and a coefficient multiplied by temperature difference. Now, a little bit about thermal conductivity. Let me see. Any of you cooks at home or not? Anyone doing cooking anytime?
Yeah. Yeah.
All right. So when you cook, let's say we want to cook, make spaghetti. Let's make a spaghetti. Now, if you want to make spaghetti, of course, we have to boil heat. We have to boil water. We have to heat water, boil water. But then, so we have, let's say, we have pots and pans. Let's say pot from copper or from stainless steel. Which one would you choose? The pot from copper or from stainless steel? Which one would you choose?
Stainless steel.
Why did you select stainless steel?
Because that's what a lot of pots and pans are made out of.
Anyone else wants to add? Because most of them, you're right, most of them are from pots and pans are made of stainless steel or so. But anyone else from a thermal point of view?
Yeah, pink copper cookware.
The copper, yes, one of your friends said the copper, yes, the copper from heat transfer point of view, copper transfers heat much faster than the stainless steel. If you want to, for example, let's say if you want to put heat 1 quart water in copper, let's say it takes 10 minutes, and in a stainless steel pot, it may take half an hour. If it takes 10 minutes, 15 minutes in copper, it will take 30 minutes maybe in a stainless steel. So that's this conductivity, thermal conductivity of copper is better than stainless steel. So from this point of view, copper is better. Copper is more expensive, of course. If you buy them, they are more expensive, but it is some very professionals possibly use this one, more expensive. But the stainless steel, of course, the good thing about the stainless steel, it always stays clean, and it all is corrosion is very high resistance to erosion, corrosion, abrasion, washing them all the time here and there. So it always keeps shiny and very good. So that's what stainless steel is, more durable and stays clean, but not necessarily for cooking. For cooking, is thermal conductivity of copper is better than stainless steel. So some people, some chefs, they prefer this one, copper, and they are more expensive. Materials which have good thermal conductivity, they are also good conductors of electricity. So like copper, for example. Now, let's go back to our formula, this Ka dt over dx. Let's write it in difference form. We always write it in like to get rid of this differential form here. In difference form, we can write it as temperature difference over length. So this is temperature difference over length. So Q is Ka over LTI plus 1 minus Ti, difference of temperature at two nodes. We can write it as U A Ti plus 1 minus Ti. So it means that we are replacing this K over L here. So U is K over L, and it is called U factor. Its unit is BTU per hour per square degrees Fahrenheit. It is called thermal transmittance coefficient, or simply U factor it is called. It makes it easier for us, just give me the U factor, and I multiplied by, this is just area, not a big deal. So give me the U factor for that material, then I multiply it by temperature difference, then I get the heat flow. That's what I want. I want to see how much heat flows, so give me just this U factor, then the temperature difference, then I will tell you how much heat is being transferred. That takes care of conduction, this piece. Now let's look at convection here. Convection is given by this formula. It is HA Ts minus Tf. It is governed by Newton's law of cooling. H here is convection heat transfer coefficient. Again, one coefficient. This is area times temperature difference. This is Ts is surface temperature and fluid temperature. Like this one here, this would be fluid temperature, Tf, and this is temperature of the surface here, because from the surface, it is transfer is taking place. So Ts and Tf, that takes care of convection. Again, units in SI and US customary system of units. It is this one. We can write it as UA Ts minus Tf. This, compare this one to this one. In this case, U is just H here. Again, introducing this U factor. Now with this, let's look at the finite element formulation for this one and then solve an example problem. Conduction, this is the same as this wall. For conduction, this wall, this is node I plus 1. Temperature at node I plus 1. Heat into this element, it is given by this. By conduction, you said it is Ka Ti minus Ti plus 1. And for this one, it is Ka over L Ti plus 1 minus Ti. Now, rewriting them at node I and at node I plus 1, the same rewriting them here. We can write them in matrix form now. These two equations in matrix form, it is like this. It is Ka over L, 1 minus 1 minus 1, 1. This is the temperature vector, and this is the heat flow vector. These are Qi plus 1 here. Like what we did in solid mechanics, everything is very analogous to solid mechanics. That's what we emphasize a lot in solid mechanics, but then everything now easily we can adapt it to heat transfer and even to a large degree for fluid mechanics. The root of all of them goes back to solid mechanics. This one, very similar to what we had before. Remember, we called this one element stiffness matrix multiplied by this is temperature vector, the same as displacement vector we had before, and this is heat flow vector. Previously, we had force vector. So this is a formula for this element. K, this is lowercase k. This one, it is U, K over L. Remember, we said U. It is UA 1 minus 1 minus 1, 1. This is called thermal conductance matrix or simply element stiffness matrix because solid mechanics dominated the field of finite element methods. So just call it element stiffness matrix. All right, this is for conduction. Let's do the same for convection, very similar to this one. For convection, very similar. You can write this HA, 1 minus 1 minus 1, 1 times temperature vector is equal to this. This one, again, using U factor, this is K is UA 1 minus 1 minus 1, 1. This is our element stiffness matrix, but for a convective element. In other words, if we want to use the language of heat transfer, it is thermal conductance matrix, the same as this one that we had for conduction, thermal conductance matrix. But this one, it is for a convective element. For convective element, we have this one. UA 1 minus 1 minus 1, 1, the same as this one, UA 1 minus 1 minus 1, 1. But U here, it is K over L, it is U, here it is simply H. And finally, in heat transfer problems, the general formula is always KT is F, very similar to solid mechanics. In solid mechanics, we had KD is equal to F. In heat transfer problems, we have KT is equal to F. This K is global stiffness matrix or global conductance matrix, temperature vector, global heat flow vector, or force vector in solid mechanics. That is the general formula in heat transfer problem, very similar to solid mechanics. That's all I wanted to discuss. Before looking at this example problem now, applying it here to this one-dimensional steady-state heat transfer problem, a practical problem actually. But any questions before looking at this example problem? All right. A typical a practical problem, actually. This is a roof of a house. It consists of, this is wood, gypsum wood, and this is insulation. This is, let's say, room, or this is our room here at, let's say, 70 degrees Fahrenheit we are given. This is this wood and insulation, and this is an attic here at 15 degrees Fahrenheit here. So this is what the problem is. Typical ceiling of a house. Assume inside room temperature is 70 degrees Fahrenheit here. Attic room temperature, attic air temperature is 15 degrees Fahrenheit. And 1,000 square feet is the exposed area. We want to find the temperature distribution through the ceiling. You want to see how temperature is changing through the ceiling, and also heat loss through the ceiling. This is 70 degrees, so this is 15 degrees. So we have some heat loss. We have to get some heating system. So we want to see what size of basically heating system we need. We are given these properties here. Inside attic film resistance. These are the U factors here. So from the attic to the surface here, U is this. The insulation, 0.053, this is through the insulation here. The gypsum board, half an inch, this is this board, its U factor is 2.22. And finally, resistance from this convection from this board to this air in the room. So these are the U factors given. I have a figure here also to possibly make it easier to see. 70 degrees Fahrenheit is the room temperature. We have gypsum board here, insulation, and 15 degrees Fahrenheit. So heat transfers from high temperature region to low temperature region. 70 degrees, 15 degrees, 1,000 feet square area. U factor is given, 1.47. This is between the air and also the this top of this ceiling here. For the insulation, it is given 0.053. For this gypsum board given, and also between this air and the ceiling surface, it is this one. We want to find temperature distribution. We want to find also heat loss through the ceiling. The connectivity table, always create this one, node 1, 2, 3, 4, 5. We have 4 elements. This is node 1 here inside, node 1, node 2, node 3 here, node 4, and node 5 inside. So you see, if we go from here, node 1, 2, 3, 4, and 5. And we have 5 elements, we have 4 elements. This is element 1, element 2, element 3, and element 4. So 4 elements, 5 nodes. This is the connectivity table from node 1 to 2, 2 to 3, and so on and so forth. And U's are given. U for element 1, 1.47, and this is for the insulation here. This is for the gypsum board here, and this is for the between the ceiling and the inside of the room here. That's it. How many degree of freedom per node? Question for you. Anyone? How many degree of freedom per node do we have?
Would it be 2?
Why 2? What are the 2? Any other ideas? Anyone? The question was, how many degree of freedom do we have per node?
It'll just be one.
You're right, just one.
Just one.
Temperature, just temperature, yes, just at this node, there is just one temperature unknown. There is no temperature in the X direction or in the Y direction. This is a scalar, it's temperature at this point. So 1 degree of freedom per node. And there are 5 nodes. So our global stiffness matrix or global conductance matrix should be 5 by 5. And this is what you see here. This is T1, T2, up to T5. So this is also T1 through T5. And it's got the right-hand side, Q1, Q2, Q3, 4, 5. Now, element 1 goes here, U1, negative U1, negative U1, U1. And element 2 sits here, element 3, and element 4 comes here. So this is the global stiffness matrix. This is the global stiffness matrix. And remember, there is an area here also. It was UA. So area, we factored this out here. This is the global stiffness matrix. Plugging the numbers, U1, it is 1.47, and U2, it is, for the insolation, it is here, and so on and so forth. Temperature vector, and right-hand side. This is node 1 and node 5. These are like attached to boundaries, but these are internal nodes. You see nodes 2, 3, 4 here. These are 2, 3, 4. These are internal nodes, so there is no, whatever Q comes here, it leaves also. So there is no, these are 0, but node 1 and node 5, they are attached to, like in solid mechanics, attached to a wall, but here they are exposed, they have fixed temperatures. So this is our system of equations, but we need to apply boundary conditions. Now, boundary conditions, temperature boundary conditions. What is the temperature at node 1? Temperature at node 1 is what?
Fahrenheit.
Temperature at node 1, it was, yes, you're right. Temperature at node 1, it was 15 degrees Fahrenheit. This was in the attic. And temperature at node 5, it is also 70 degrees Fahrenheit. So to apply the boundary conditions here, this is our system of equations. I have written, these are non-homogeneous boundary conditions, homogeneous when it was 0, but these are not. These are known temperature values. At node 1, temperature is 15 degrees Fahrenheit. The way that we apply, this is a non-homogeneous boundary condition. The way to apply this is by correcting our first equation such that it gives T1 is equal to 15. So I've shown it in red so you can see that this first formula here, this first line, I had to change it to 0. This one is multiplied by 1000. I have to make it 1 over 1000. So when multiplied by this and then multiplied by here, it gives T1 is 15. That's what we need. T1 is 15, you said. It's in the attic. That's how you apply the boundary conditions, the non-homogeneous boundary conditions. For homogeneous boundary conditions, remember, we just removed the row and column associated with that node. But for non-homogeneous boundary conditions, we do it like this. We correct it such that it gives T1 to be 15. Do the same thing for T5. T5 also, we said that T5, it is 70 degrees. It is the room temperature. To do this, this one, we have to make it 0. And this one, I have to make it 1 over 1000 because there is 1000 multiplied by this makes it 1. And then it gives T5 is 70. That's what we wanted to get. That T5 is 70. That's it. This is the number. It is ready to be solved by Nastran. VMAP creates this one, hands it over to Nastran. Nastran solves it and returns this temperature distribution back. These are the temperatures. This is the attic 15, room 70, and these are the temperatures that we wanted through the ceiling. All right, any questions before looking at part B of the problem, which was to find the heat flow through the ceiling? Any questions? All right, no questions. This is the formula that we have. Q heat flow is UA delta T. For element 4, we find it for element. So element 4, this was element 4 here, which is element 4 here. It is here between this surface and this one here. So this is 70 degrees and temperature at this point, let's see what we got. This was 68.19. So this is for element 4 here. This is element 4. 70 degrees and 68.19 here we got. UA delta T. This is U for element 4. Area 1000 delta T. T5 minus T4. Temperature difference here. 2660 BTU per hour. This is the heat flow through element 4. You could do the same thing for other elements. For example, I did it for another element also. You can do it for other elements. Select, see what you get. For element 1, this is element 1, that element 1 was here from this attic to this here, to the surface of this inside of the attic here. This one, 15. And temperature here that we found, this was 16.81. So for element 1 is 15 and 16.81 UA delta T. This is U for this element 1 area, and delta T, we get the same 2660 BTU per hour. That is the heat loss through each element. This is a steady state problem. Whatever heat passes through this element, passes through this element, the same as here, and then goes to the attic. So this is a steady state, and the heat flow through element, all of these elements should be the same. That's what you see here. For element 4, we got 2660, and for element 1, we got the same 2660. All right. I don't want to go any more. This is for our next week. I don't continue and cover any more material. Any questions, anyone, about what we discussed? All right, I don't see any questions. So this is briefly what we discussed, chapter 13, heat transfer, one-dimensional, steady state, and direct formulation. Later, we are going to use variational method, more comprehensive one. This is a simple derivation we did for conduction and convection, and we looked at one example problem. Before ending our discussion today, reminder about our quiz next week on Monday. It will be November 15th. You go to Canvas. There is no need to come to Zoom. Directly go to Canvas at 10 o'clock. It starts and finishes at whatever 30 minutes or 40 minutes. It will show you how many minutes we have. 5 questions, 2 points each, and make sure that your internet works and everything works fine so you are able to take the test. If not sure, just go and take it on campus. It starts at 10 and finishes in half an hour or 40 minutes or whatever it is. 5 questions, 2 points. It covers all chapters, whatever we covered after our midterm exam, which was frames, plane stress, plane strain problems, and also chapter 7, which was practical considerations in modeling that we discussed today, but not heat transfer. This is about the quiz, and also for the, I will meet you after the class at 11 o'clock. So 10, you take the test. We have some students with from DRC, they take the test, but then at 11 o'clock, we will meet to continue with our heat transfer discussion. That would be for our class at 11. On Zoom, I will meet you. And then for the project, we don't need to come to Zoom. You work on the project. We discuss about also the constraints. Make sure that you select the right constraints in your problem. With this, if you have, of course, questions, always stop by during my office hours. Otherwise, I'll stop here, everyone. Have a good rest of the day. I will see you all on Monday next week at 11 o'clock for our class. Take care, everyone.
Thank you, sir.
Thank you.